Okay, all right. So if you can see my screen, you can just type it in the chat so I know you are up and then we can move. All right, so for day 3, what we'll be looking at, yeah, thank you very much. So for day 3, what we are looking at is verification plots. So I've had a couple of questions from a lot of subscribers from MeteoData and then students alike, researchers alike, and they want to see how best to produce some verification plots like all these Taylor diagrams and the rest in Python. So in that case, we decided to put this material together, and then we hope that it will be enough a resource to help somebody in time of need. All right, so what we are addressing today is a verif package, which is a command line tool. Actually, this by default runs on the command line, but then you can integrate it into your Python environment and then make use of it for the verification plots and analysis. So to install this, you can just use pip install verif. You can also download directly from the repository and then host it on your PC and just run it on your command line. Now, we've also attached a verif help file to be enough a guide. So I'm just going to run through this. Of course, some write-up here to assist you on what verif is and how it works. I'm going to restart my kernel so that we start from the scratch. Okay, so in order to display this verif help file directly on my matplotlib, not matplotlib, my Jupyter notebook, in order to visualize it directly. So in order to visualize that directly on the Jupyter notebook, we would have to import the ipython.display. We go into that package and import just iframe and the display. So the display is to help us display the PDF. The iframe is to create more like a canvas within which is displayed. Okay, and then the file is just verifhelp.pdf. That's the file name. And then we create the iframe with the iframe package. We create the canvas. We pass in the file here. We specify the width and then the height, and then that is enough to at least show our PDF directly. And so this is just a README. You can go through. It's also hosted on the GitHub. And so if you want some further details, you can just have access to it. So if you go onto the GitHub page, so the repository for the joint MeteoData PY4CA webinar series has it. So the notebook is hosted in the day 3 IPython notebook, and then there's the help file, one here, and then also another one in the image directory, so you can access it from there. All right, and so this provides a whole instruction on how to install it in every medium, that's Ubuntu, Windows, from source, and so on, and then the tools, how it works on the command line. Now this, like I said, it works on the command line. So we would be finding a way to integrate that into our Python environment. Simply not necessarily creating any extra, add-ons and packages and all that. I'll just look at a few of them, but then you can always, take time to look at any of them. And if you have any issue, get back and we would be able to help you out. So a quick look at the structure is, that's how the data structure looks by default. The simplest way you can have the data structure is that the first column should be the dates, the second would have the observation, and then the third, the forecast, where in this case, observation forecast are used as a representation of, let's say any two data sets you want to compare, one being the real one or the observed one, and then the other one being probably a simulated or, modeled or whatever it is. And then the very first two rows by default should contain the variable, and then in this case, the variable name, and then the units of the variable. Now, the package is built to sort of interpret that already. And so if you're going to work with, say, NetCDF files, how do we, read those information and then create something like this in the structure for the data to be able to interpret and then make meaning out of it? Okay, so In order to do that, this is more like a tabular data. So we'll be making use of the pandas data, the pandas data frame or the pandas package. So in here, we are importing pandas as PD. So we import pandas here as our PD, and then let me just run everything from top again before this line. Okay. So we import pandas as PD, we import our numpy, which is numerical Python, as NP. And of course, I've already explained what the filter warnings does, so that it ignores all the warnings. With the exception of all, we would see some command line warnings, but those are no issues. All right, so we run this, and then we are going to use a pandas to create this data frame structure. Okay, so there's also a sample data contained in the verif examples, and then one of them is a sample data. All right, and so I'll just read that so we see how the data structure looks. So there's a sample data structure that's a test data from the verif developers. So that's data that contains the date, the lead time. These are more like forecast data. So the lead time, the location in terms of longitude, latitude, the altitude, the observed data, the forecast data. All right. But then, like I said, all these ones can be overlooked, and then the key ones needed in this case for just a simple representation will be the date, the observation, and then the forecast. All right. So of course, once we have this sample data, we can again just use a pandas data, package. We read the CSV, which is the file itself. The file is separated by tabs. So each column is separated by tabs. So we indicate the separated tabs. We skip the first two rows, which are the headers, so that we can see what the data structure itself is. And then we assign headers to be 0 so that no headers are given. And then we pick just the date, the observation, and then the forecast alone. And then this is how the data looks. All right. And of course, we can run this and save it from the PD data structure. Once you've already read your data to a variable, say A1, you can just use the .csv to save that data to a new CSV. And then, of course, we indicate tab separations. That tab delimited, more like a tab delimited file. So we have tabs as separations. Okay. So that's one key thing we need to understand. Now, in this case, we can import verif, which is the package we'll be using. But then if you build it directly onto your command line interpreter, then you can ignore this. And once you call this in Jupyter Notebook, it works just like your command line interpreter. So pick it from the default, directory, and then use that to run. And then we actually will make use of this base because sometimes you might have a file which has a long path. For instance, there's data, verif examples. All these are the path to the file. Now we want, let's say, the file to be saved only with the final name, so we'll make use of the base name. So base name, let's say, for instance, this is my file. Once I import base name and then run base name on this whole file path, it just gives me the final name, which is the sample data. Okay. Okay. I think the import verif is taking some while to run. Okay. Yeah, that's it. So you have the sample data, which is just the final file. So you don't necessarily need a path. All right. And the reason why we would want to do this is that when you use the verif to plot, it's, once you list the file path together with the name, it would combine all that and give that to your legend. It would assign that to your legend. And so you would want to just use the final one. Okay, and so there's one way to do that using the base name. All right, so let's say we want to run. So I believe this is enough for the background. Okay, so I'm going to now perform a sample, verif computation, which is the mean absolute error using two sample verif data sets. So in my verif folder, I have within the data folder, there's verif examples folder, and then there's a data called raw.txt, and then there's also kf.txt. So I want to compute the absolute error between these two. All right. So what I do is, if you go back to the documentation, you will be able to interpret that. So we call the verif package, which is a keyword, meaning we are invoking verif here in order to perform the error assessment. And then we specify our first file type, the first file source, and then the second one. And then we indicate the method. So the method we want to employ here is a mean absolute error. Okay, so with the mean absolute error, we are going to compare the error assessment between the two. And then the minus F, which is a switch, indicates that we should save the output to this file. So we are saving the output to try.pdf. So if we run this, it might take a while, but then it would run and give us an output in try.pdf. Okay. All right, so let's just wait a little while and see what the output would be. All right, so while that is running, if you also need any detail, all right, I think this is done. So the output was try.pdf. Let's see what try.pdf contains here. So we pass this here. I've already explained this. So with the iframe, we can just call any file and then view it directly on the Jupyter notebook. Yeah. So these are the absolute error within the two data sets. So within the raw.txt, there's an observed file, there's an observed data, and then a forecast data. So it computes the absolute error per the lead times. All right. And then it does same within the kf.txt per the various lead times. Okay. So with this, you can simply, do any error assessment. Now, if you are not sure on how to maximize any tool, you can just call verif -m, which is the method, and then specify the method, and then this should give you some detail on how it works. Alternatively, you can go into the verif help file and then get some extra information. All right. Okay, so exactly. So this gives you just some help. Now, these warnings you are seeing here, just ignore them because currently the version of verif I'm having should work with NumPy within this range, but then the NumPy package I'm having is 1.23, which is equal to the highest threshold, and so that's why it produced the error. So it's detected 1.23, but then the verif needs something between this 1.16.5 and then 1.23, but then it still works. All right, it's just that the version control just produces this warning. That's all. Okay. Now, can we run the same function on a file, let's say a series of files at the same time? Of course, it's possible to do that. So this is where we are now going to incorporate the command line approach into the Python. So in Python, when you use the for loop, for instance, we have this for files in this list of files, we should just print the files. So that's going to print all the files one after the other. So first it goes into the first item, it picks the first item, prints that out, goes into the next item as long as the loop is not completed, and then prints the second item out. So this is just typically printed, but now we are going to implement the verif on each and every file. Okay, so for every file, we try to run a particular, let's say, verification computation on that without necessarily going to type them one after the other, which will be too long. So we want to just look through. Okay, so we make use of our for loop. So for files in the same data set, now we run, instead of printing, we invoke our verif function here again. And then on the command line, bear in mind, these files in Python, when I print these files, it will print it as files, but on the command line, the files need to be preceded with a $sign so that it knows that it is a variable that has been assigned a value. So in this case, the files would be the respective files up there. So we call the verif, which is a command line interpreter. Again, that's preceded by the exclamation, telling us that we are running this on the command line. And then we call the files with a $sign preceding it. And then -m, which is the switch for the method. So in this case, I want to compute the Taylor, I want to produce the Taylor diagram, okay? And then the -fs tells us the file size. So 10 by 8, that's 10 inches by 8 inches in terms of the width by the height. So 10 inches width, 8 inches height. And then -f is where it should be saved to. So currently I'm saving this into the image directory, and then I don't want to use this whole name, but rather I call the base name on the files, which I explained earlier. That when you run the base name on the files, now you notice that in this case, the base name on the files didn't need a $sign because this base name is a Python-based approach. So we call the base name on the files so that it gives us just the final file name. But then since we're going to use it on the command line again, then we needed to place that in the curly brackets so that it's treated as a variable that is invoked together with this. And then we'll have the img slash that particular file name .pdf. And so, for instance, in the first example, we'll have this file saved as into the img folder and with the name sample underscore data.pdf. And then it will have a title. I mean, you can give it any title. Well, for this point, I decided to use the title, say D. In fact, in Python, we can equally enumerate. So we can enumerate this. And then we know enumeration would always give an index and then the variable itself. And so we are going to pass in here the title as, let me format this as a string. So we print the I. So position 0 will be printed as the title for the first one. So title 0, second one, title 1. And then we just run this, and this should produce our Taylor diagrams. Okay. So with that out of the way, means when we take any of the files, for instance, in the img sample data, we can visualize that. Same way, img raw.txt.pdf should also give us a particular file. Okay. All right, so let's just wait for the output, which will take a little bit of time. All right. Okay, so that's done. And then, of course, we want to display this directly in here. So we've already imported this. In fact, you don't need to import this all the time because we've imported it once. All right, so I mean, we can just quickly call the iframe and then just run that. And that's the Taylor diagram. Okay, let me minimize this so we can see it clearly. All right, so this tells us there's a Taylor diagram. So between the one column of observation and one column of forecast, we had a correlation of 0.93. All right, and you know how to read the Taylor diagram. So you draw a line parallel to this to meet the correlation. That gives you the correlation value, and not just the correlation, but also it gives you the standard deviation. So if you trace this parallel to your standard deviation, you can see the standard deviation value for the forecast, and then this is that of the observation. The orange square is that of the observation. That's the standard deviation for the observation. Now with this, you can tell whether it is underestimating or overestimating. So when you take your standard deviations, you see that this is lower than that of the observation. So there's some bit of underestimation by the forecast. And not just that, you can also get your centered root mean square error. That's the continuous, grayish lines. It tells you the centered root mean square error. And so this is between 50 and 100. That's about 80 millimeters sort of root mean square error. And then if you take your minimum CRMSE, you can also see what the value is. That's the dashed, orange line, comparing that of the observation to the forecast. And so simply you can just use this to generate what's the name? You can use this to generate the Taylor diagrams and then the various kind of verification plots. All right, so I think I did something in here. Okay, so this is being interpreted directly on the on the command line, so we don't necessarily need to give the formatting, unlike in Python, which what we would have done. All right, okay, so now we have that for the sample data. So can we also check what that of the raw.txt, because we created a base name on that file. So if we run this for raw.txt.pdf, we should also see what was produced. Okay, and you notice the difference. And so this is from the raw file. We have a correlation that's less than 0.9. That's about 0.85. And then in the raw file, there's rather an overestimation, right? because this red point is above the, the mark of the observation. Exactly. And so once we generate a Taylor diagram, we can also generate the error plots, and it's quite easy. But then one of the things you need to understand about the Verif package is that I think by the builders, there's actually a bit of bug in there. So if you run the error diagram directly, or you run the error computation directly, the value it gives you is actually the negative of what it should be. So in places where you see an overestimation here, if you run the error value, it rather produces an underestimation. And so there's also a tweak around it to help. All right. Now, what if we are going to repeat the same procedure this time? We don't want to plot just the Taylor diagram, but want to have, say, the Taylor diagram on one side, the error plot also on another side. Of course, that is possible. That can be done. So that's also like a tweak. So in this case, we are going to import our matplotlib.pyplot as PLT, because this would help us create the various canvas or the various panels, which if it's two or more, we can use the matplotlib.pyplot to create. And then we also have the matplotlib.image, which would help us read an image. So there's, for instance, a PNG file. We can use this package to read the PNG. And then we would use the top one to place that PNG into the context of the panel. All right. Okay. So we would want to, all right. So let's say I'm going to run this. Okay, I already have this file somewhere. So let me not even bother with this one. Let me just take this part off and then rather run it from here. So I'm basing this on the fact that we've already explained what the subplot does, how the subplot works. Right. So from the previous lecture, we already said that with the plt.subplot, you can create, the sort of panels already before you pass in your plots. So in here, we have a subplot that contains two columns, and then the figure size of, say, 15 by 8. So we are going to have, let me just run this part alone so that we see how the plot would look. So when we run this, this tells us how the panels would look. Okay, sorry, I need to run this one first. Okay, so we have these two panels, one on the right, one on the left. Now, if we also want to, rearrange them, there's all the what do you call the grid spec packs, which is the extra arguments you can pass in so that you can shift it a bit. We'll see all those if this time will permit. All right. Okay, so we have the first part done, and then now we are going to look through based on the for loop. So for files in these two files, all right, we would just create the Taylor diagram, for instance, and then place it in one, and then create also the arrow diagram in the other one. So whilst we are looking through any two of these at any point in time, first what we do is we use the verif, we invoke the verif command over that particular file. So if it's raw.txt, verif over the raw.txt, and then we pass in the method. And the method here is we want to generate Taylor diagram. So -m Taylor. That means to generate the Taylor diagrams. Then we give the file size, in this case 10 by 8 plus 10 inches by 8 inches. So 10 inches width, 8 inches height. And then the file name, in this case, I already explained that the base name of this will produce as a last name. So this should be saved to the file raw.txt.png. All right. So this will create the Taylor diagram and save it into a file. Now we are terming that file just as a temporary file. And since it's a .png, we can then use the mpimg that we imported, the matplotlib.image. We can use that to read the PNG file from here. All right. And this is actually a Python line. So in this case, we don't need the curly brackets like we did for the command line interpreter. So we would run this on the base name of the file .png, and then it reads that PNG file, and then we pick the particular axis we want. So in this case, the axis, we want this to be on the first one. So axis 0.imShow, and then we show this variable that we've created, which is the PNG file we called. And this will show that PNG in the left panel. Now we can give it a title. We can also clean the axis. So if you don't turn the axis off, you have the plot, all right, but you have the axis around them. And then we also run in the second part the same function, but then this time we change the Tailor to error, so that this will produce the error diagram, not the Taylor diagram. And then the error diagram should be on the right hand side. So with the same procedure, now we read the error diagram.png, and then we pass that to the axis 1, which is the right hand side, give it a title B, set the axis off, and of course we can delete this. Now this like a command line interpreter, so we can use the del to delete the file. So I'm running this, which should take a bit of time, but then it will give us an output. Okay. Right, so one part is, I believe one part is almost done. Okay, so it's now moving on to the second file. Okay, so one part of the second file, the second part waiting. Okay, I believe both are done, so we should have it soon. All right, and that's it. Now this shows just the second one because I'm still showing the plots within the loop. So this is for the the sample data.txt. There's a sample data, that's the second one. And so that's why we have the sample data showing here and then also here. But then, of course, the raw has also been produced. So if we use the same approach we're using to visualize our file, so if I now run this on the raw, I expect that this would have been overrated because in the first case, we had this being just a tailor. Now we've produced another raw.pdf. Let me check if it was in the IMG. Okay. All right, so that was in the IMG. So, okay, let me just copy the line that produced that. Okay. And then create a new cell above this, pass this in here, and then we don't need the IMG because it's just directly produced. Okay, where's the file? Let me see. Oh, okay. So we made a mistake. It wasn't really a mistake. What we did was we didn't save this file. So after producing this, we didn't save it. That's why we didn't have it showing. Okay, so this might take a while, but let's just save it. Let's see. So plt.savefig, and then save the fig to the base name of the file. And then add the .pdf, so that shows us the PDF. Okay. All right. Okay. All right. So once that is done, we can be able to view this in real time directly here. So I'm just going to allow that to run while I move on with the other one. Okay, so now in this case, what if you have your own data and you want to work with that? Now in this case, the first part, we're using the sample data, which is already structured. But if you have your own data and you want to place it in the structure, if it's not in the structure that Verif needs it to be, it wouldn't work. And so if you have your own data, you want to structure it the way the Verif file, the package will be able to interpret the data. And so an easy way to do that is, we can always create, using pandas, we can import pandas as PD and then create a data frame. Now this, I've already imported pandas, so just run this first line. And if you run this, this will create a data frame for us, but then it's just going to be a blank data frame containing nothing. And so if we run that, we call that as the variable out, and then we can pass in just a dummy set of arguments. Okay. Now this is, I'm just passing some dummy values. So that's how the empty data frame will just look. Now I want to give it, I'm creating a new column called observation, which is OBS, and then passing in the values just 0 to 9. Okay. And so with this, let's see what the out would be. So there's just the output. All right. Once we have this out, bear in mind, if I have my data wouldn't come with the headers. And we already said from the beginning that the pandas, the very data structure needs at least the first 3 to be headers. So if my data is only this, how do I create those headers? There are different ways around it, but I'm just going to use one simple approach. Okay, I think this file is already done, so let's see how the raw.txt looks. Okay. All right, so that's what we created for the raw, and then this was that of the sample data. Okay, and then I'll come back and explain something from this so that we understand clearly what happens in here. All right. Okay, so the question was, how do we create those arbitrary headers in here? So what we can do is, since these are indexed, okay, since they are indexed as positions, we can of course create negative indexes too. So by creating this using the .log, all right, so out.log -3 and then passing just a value, and then we just create it out. Now this will then create the variable, the input for us, and then it would specify the index as -3. Oh.
With a jacket over your head. Have the teeth around your waist and instead of letting the buckle in front of you.
So we would have the data still sorted in this order, and then the one we just indexed will still be given as negative. But then because we have this, we can sort the index. So I'm going to just pull these ones out from here. Okay. So if we have this, we can sort the index first. Okay, and then the negatives will come up. What if I then add, say, a -2 in here? And say, okay, now over here, we're just going to pass in PY4CA. Right. Now you see, once I sort the index, because this is in no particular order, it just, will produce any information I need. But then we can reset the index, right? You get it. And then once we reset the index, we can drop all our indices and we are good. And that's one easy way to do that. So by resetting this index, it means we still give them the value 0 to 11, and then we'll delete this this index that was there. The negative values have been included. We don't need them in here. So we can just drop the index. Now this is index here is a column. So we'll need to specify that it should be split or it should be dropped along that particular column. And then that's it. And then we have this re-index properly. Okay, so this whole thing is what we've just built. There's like a tweak around making the verif package work for you. Like you just build a function, make it functional once, and then you can always use it. And so we have this function called file to verif format, and then it would need input of date, the observation, and then the forecast, and then the variable name. If you don't specify it, by default, it will just be RR for rainfall, and then your unit, if not specified, we just use mm for millimeter. And so, of course, we already have gone through this. So whatever your data is, once you create a data frame, it would use the date you pass in, it would keep that under the column date, keep the observation under the column observation, and then the forecast, sorry, the forecast under the column forecast. And then when we are done, now, just like we did for the very first part, this time we are creating the variable not just over one column, but then over multiple columns. So we go to the locator -3, then from the 0 all the way to 2 end. And since we are following the structure, the first one will be the pound sign or the hash sign. The second one will just be the variable with a colon, and then we pass in the variable name as a string. So in this case, the variable that you entered, we pass in here. The unit, we do same for the unit. And then we also pass in the headers, date, observation, and then forecast. And this is purely because when you look at it from here, this is how it looks. So the dollar variable, then the variable name, dollar units, the pound or the hash sign unit, and then the unit category given, or the unit name given. And then after that, there's date, observation, forecast. So we just tweak that using pandas down here. Okay, so this is what the pandas will do in here. And then once we are done with that, we sort the index, reset the index, and we drop the index. And then we are left with just the data in the format of the date, forecast, and observation. And then we return this out. Okay, so I'm going to just use this as sample data. So for instance, I have these locations as my nested list created, and in the location, the first one is say Tema with these coordinates, Kumasi with these coordinates, that's longitude and latitude, Tamale with this coordinates, longitude and latitude. Now these are locations in Ghana. So I'm just going to use this as demonstrations. And then of course, once we look through this, when we use the enumerates, we can print out the index and then whatever the location is. So of course, this is just giving us a fair idea of when we are looking through it, what we'll be seeing. Okay, so I'm going to use this on the Africa data we had. So we import xarray as xr, and then we open our Africa crew data.nc, and then we read the variable PRE, and we assign this to DA underscore crew underscore PRE, which is the crew precipitation data set. So we can see what the output is from here. Okay. All right, so this is taking a while, but once it's done, you will see the output. Okay, and so there's our precipitation data, time, latitude, longitude. Now, in this case, I don't have two data sets, I just have one data. So I'm just going to do some assumptions here. I mean, that's not the case, but of course, when you are doing a verification or validation, means you are comparing, say, two data sets or let's say a co-located point. But what I'm going to do is I'm just going to pick the individual points, say Tema alone, and then I would have the observation be in the entire Ghana, which of course it doesn't really make any sense, but just to give us two data sets to compare. All right, so I would just take the entire Ghana data. So I'm going to slice that. For instance, we have DA underscore GH. Now we select along the longitude, we create a slice from negative 3.5 to 1.5, which is a range of longitudes, and then the latitude from a range of 4.5 to 11.5. And then once we have this, this is going to be a spatial data. So we want to have a time series. So we find the mean over the latitude and longitude. And this gives us just a time series. So let's see how this looks from here. And then we can see what the D underscore GH contains. Right. So that's just time data, which of course we can visualize and we see what it contains. All right. So there's just a time series. So I'm going to compare every individual location to the time series for Ghana, which of course I've already said it doesn't necessarily make any sense, but just to give you a fair idea how to use the tool. Okay. And then we also have our locations here. I'm going to look through the locations. Already I've created the time series for Ghana. I'm going to look through the locations, and then for every location, I select where the longitude within that data array is equal to the particular location's longitude. The latitude is equal to that particular location's latitude. But then there's a tendency that these points will not be found in the latitude and longitude, because when you look at the intervals, these are 0.75 and 0.25. But these are 0.7, which might not be found in here. So we are using the method nearest to get the nearest point or the nearest neighbor. So if this location is not there, pick the closest point to it as a representation of that location. Once we do that, at every iteration or at every loop, we'll have the data for that particular location alone. Once we've selected a point location, we are expecting that it will just be a point time series. All right. So once we have that, now we are going to call our file to vary format. Okay. And then this is the function we built. We said the function needs date. All right. Now you can read the date from the file and pass that in here, and that should still work. Alternatively, you can use the pandas to create a date range. So what we did here was to use the pd.date range, and then we passed in, let's say, a default start date. Okay, so this can be any date. Now this is say from 1980 January 1st, and then since we are not we are not so certain of what range of years we would have, we can just use the periods, so that this will just be periods created based on the length of our data. So I pick the length of the Ghana data and use that to generate the period. So think of it this way. We have this part alone, okay? So our pandas data, our date range, we enter the starting year, the starting year, and then the periods, and then this will create the dates, sort of daily dates till the end of that period. Okay. Now with this, we don't need to worry our heads with what the starting, the ending is. No. And of course, the date is not going to be used for any computation in here. It's only the data we need, but we need to specify the date because the verif understands that the data structure has the date as the first. All right. So once we do that, we can also format. We use the strip format, which is to format the time or the date time into. This means year, that's 4 digits year, 2 digits month, 2 digits days. And that is the structure of the data. And that will be for the date. So what we have here will be red, reformatted as year, month, date. Year, month, and day, and be assigned to the date column. All right. When that is done, whilst we are within this loop for the first location, the data that we pull out, when we get the data, for instance, let me just, okay, so I don't want to run this here. So if I call that particular location and we have all the time series for that location, let me use the Ghana as an example. So let's say we have the DAGH. Okay, so there's the Ghana data. So just dot values would produce all the data values, all right? And then we then, formatted this. You can format or decide not to format. I just decided to format this as integers. So just add the dot as type and then call this integer. So these are formatted as integers. And that's it. All right. But you can decide to maintain your floats. And I believe that should also work. Right. So we've already entered what the date is, what the observation data should be, what the forecast data should be, and then the variable name. Okay, we just specify that this should be, say, variable RR, and then the unit should be millimeters. Okay, and this whole thing will be formatted into the verif structure and assigned to the variable out. And then with the out, there's a pandas data frame, so we can just add the .csv. And so out.to_CSV will create this as a CSV file to the file name, the particular station. In this case, because we are looking through the log, remember that when we run this, the log at every instance is any of these stations with all the coordinates. So if I want just the first element, the log 0 will give me, for instance, just a Tema alone or Kumasi alone or Tamale alone. All right, and then we indicate that between any of the columns, they should be tab separated. So they'll be separated with tab spaces. And then we also indicate that there should be no header. All right, so aside the, pandas data structure by default. Okay, now I think I can run this. Let me comment this and run that so that we see what the output is. Okay, I need to go back and run my function. All right, come back here. All right, so now I think I can use this to explain. So when you take the output, pandas data structure by default has its own header, all right, which whilst we're reading was creating that. So we want to drop this header and drop the index so that we are left with just the input here. And of course, this first would then be our own defined header. And so by saving this to CSV, we specify that there should be no header, so it would ignore this header. There should be no index, so the index would also be ignored, and then we only have the data saved into the CSV. Okay, so once this is saved to the CSV, bear in mind it was just the file name. I didn't add any extension. So once we have that, it means we can call the verif, and then we run the verif on all the files. So in this case, Tema, Tamale, Kumasi. Right. This I'm not going to run just one file alone. I want to have the output of all three of these stations, all these three stations on one plot. All right. And then I specify what method I'm going to use. And then in this case, the method is a Taylor diagram or produce a Taylor diagram. And then the file size 15 inches by 8 inches. It should be saved to the file try.pdf. Okay. And we can just run this. When that is done, we can then, see what was produced in the try.pdf using, we've already run this first line multiple times, so we don't need to run that again. Okay. So when that is done, we then see what the file contains, and then you see the output and how simply we can use sort of integrate the verif into the Python. Okay, so that's done. We run this, and then we have our output. Okay, and so these are all three locations, and this is telling us that, of course, like I already explained, what we did doesn't make any scientific sense comparing the individual stations or a point to an entire country. So we picked the entire Ghana as a point and then compared individual locations, say Tema, to the entire Ghana. It doesn't make any scientific meaning, but just to see how this works. Okay, and so this tells us that at least that of Tamale seems to have a higher correlation with the entire country, followed by Kumasi and Tema. And the basic reason for this, we know that Ghana has different rainfall regimes, so bimodal, unimodal, and of course the rainfall magnitudes will change rapidly. So I expect that the stations that seem to be having lower rainfall would be closer to the mean for the entire country more than the ones with, say, probably more events. So that's the only meaning for this. But then, like I said, it doesn't make any scientific sense. It's only for the purpose of usability. Okay, and so the next part is, now we want to produce not just the Taylor diagram, but then just like we said, we want to do same as the Taylor diagram and then the error diagram. And I've already explained that from the first one, so I'm just going to use the same approach. Now this time, what I'm doing is I create the verif format, and then my observation is, say, the various observations against Ghana. No, it should be the other way around. So the entire Ghana should be my observation, and then the various locations should rather be the forecast, so that we are matching all of them against the country. Yes. But then, like I said, when it comes to the error diagram, there's a bit of bug in here. So there's a bit of bug, so you need to rather reverse them in order to get that. Okay, just a minute, please.